We are working on actual applications of higher order derivatives. In the last video, we saw an application of velocity and acceleration, and I gave that example first because that one is usually the easiest one for students to understand, but there are more applications than just that. So let's see another application of higher order derivatives. An efficiency study of a morning shift at a certain factory indicates that an average worker who arrives on the job at 8 a.m. will have produced Q of t given by negative t to the third plus 6t squared plus 24t units t hours later. So this tells us how many units that an average worker is going to produce after 8 a.m. in the morning, depending on what hour they are in their shift. In A, we want to compute the worker's rate of production at 11 a.m. And B, we want to figure out at what rate is the worker's rate of production changing with respect to time at 11 a.m. I suggest you pause the video and see if you can come up with the answers to these problems. Okay, in part A, we want to compute the worker's rate of production at 11 a.m. So our key word here is rate. We know that if we ever want to compute rate, then of course we're going to take the derivative. So our rate equation, which I'm going to label as R of t, comes from the derivative of our quantity equation, Q prime of t. This is in our preferred format of a constant times x to some power, so I can use my 4 shortcut differentiation techniques. Gives me negative 3t squared plus 12t plus 24. So this is my rate equation. If I want to figure out the rate at 11 a.m., I just need to substitute the corresponding number. Well, if at 8 a.m., that means our time is equivalent to 0, that's our initial starting time, then at 11 a.m., our corresponding time is going to be 3 because it's 3 hours later. So we need to figure out what Q prime of 3 is. So that means I just substitute 3 into all the t's in this equation and simplify. So this gives me negative 27 plus 36 plus 24. And when I add all these together, we get out 33. So Q prime of 3 is equal to 33. But this is an actual application, so what does that actually mean? Note that in rate, it is something per something, and we are talking about the quantity of units produced. So this is 33 units per our time allotment, and our time allotment here is in hours. So at 11 a.m., this average worker is producing 33 units per hour. Okay, moving on to part B. At what rate is the worker's rate of production changing with respect to time at 11 a.m.? Well, at first glance, you might think, didn't I just compute that? But pay really close attention to the wording here. Notice it says rate twice. At what rate is the worker's rate of production changing with respect to time? So if it says rate twice, that means we need to do our rate equation twice. Now, in the last example, we figured out our rate equation was equivalent to the derivative of our quantity equation, which gave us negative 3t squared plus 12t plus 24. So if we want to know the rate of the worker's rate, that actually means we need to do the derivative of my rate equation, or the second derivative of my original equation. Now, this is in preferred format, so I can go ahead and just take the derivative of it. That gives me negative 6t plus 12. If we want to know what's happening to it with respect to time at 11 a.m., then I just need to plug in the corresponding time. And we already know that that corresponding time is equal to 3 at 11 a.m. So I need to figure out what q double prime of 3 or my rate derivative at 3 is going to be. It gives me negative 6 times 3 plus 12, or negative 18 plus 12, or negative 6. So we can do the math behind it, but what does that actually mean? Well, since we did a rate equation instead of something per something, we're going to have two pers here. Something per something per something. My first thing that we're talking about here never changes. This is negative 6 units. But then this is per my time allotment of hour. And then again, per the same thing, per my time allotment of hour. So my official answer here is negative 6 units per hour per hour. That's what's happening to my rate of my worker's rate of production with respect to time at 11. Now this is where students start to get lost. What does this actually mean? Well, think of this kind of comparison to your acceleration equation. Is my average worker speeding up at this time, or is my average worker slowing down at this time? Since my answer is negative, that means my average worker is slowing down at 11 a.m. That means he's producing less and less units. And to be exact, at 11, he's producing 6 less units. And so here is another application of why we might need to take more than one derivative.